Say it again. Yeah, there's a worksheet for this one. It's attached.
Oh, no.
You can see it. Okay, so this first lesson, it covers periodic phenomena. Okay, so this is kind of an intro to trig. You can tell that our unit 3 is going to be mostly trig. That's generally how pre-cal works. The first semester, you spend a whole lot of time on algebra, which is why we're reviewing the college algebra course, right? The second semester, we usually transition into trig. In the past, Pampa ISD has offered a pre-cal credit to kiddos who only had taken the college algebra and hadn't taken the trig yet. And so pre-cal without trig is kind of a very sad existence. It's college algebra, right? So that's where we're headed with this whole unit 3 is into trig functions, trig identities, the trig, right? And this is essential for calculus. So what we do here is going to carry forward. This is why I taught you a 6-week trig unit in Algebra 2. Just in the event that I had anybody jumping from that Algebra 2 course straight into calculus. And I do have a couple of them. And so the only trig that they got was that 6 weeks at the end of the school year last year. So consider yourselves really fortunate to have a semester to dive in here and really understand. We're going to build on what we did. Okay, but we're not going to start speaking with trig words like sine and cosine and tangent. We're not there until tomorrow. So this lesson is just recognizing periodic phenomena, recognizing real-world applications of things that repeat. Okay, a periodic relation or relationship between two variables occurs when the output values demonstrate a repeating pattern over successful equal length intervals. So I'm thinking in my head things that are cyclic. Okay, the revolutions that a microwave tray makes while I'm heating something up. That's cyclic behavior. If you look at this particular graph, you can see that this period or this cycle is repeating. Can you tell? Okay, in a real life situation, what does that look like to you? Can you think of a real life graph that would look like a heart monitor? That's exactly right.
I'll just say dry.
Says, are you still planning to study like medical? Okay, so when people study for like heart murmurs or my dad was born with a hole in his heart and they found it really, really quickly because they were able to look at his EKG, look at the period. It should be really regular. It should be repeating. So when it's not, they know something's wrong, right? The period of a periodic function is the length of the x values that it takes for the function to complete one cycle. So period is going to be length of x values that it takes to complete one cycle. So before the cycle gets ready to repeat again. I've kind of already marked on this example 1, but what do you think that the period might be here? How long is the cycle? 4. And you could find that by doing the end minus the beginning of the cycle. I could do 7 minus 3. I could do 3 minus -1. Both times I get 4. Okay. So the function f is periodic with a period of 4. A portion of the graph is shown above. Draw 2 additional periods. 2 additional periods. So it looks like for the next 2 units, it's going to go rise 1, run 1, rise 1, run 1. And then it kind of levels off from 9 to 10. And then from 10 to 11, it rises 2, runs 1 in the downward direction. So without a ruler, that's kind of the best I can do with an Apple pen. It's not great. It's not terrible. You agree? Kind of have the same information there? Okay. So example 2, it says a portion of the graph of the periodic function g is shown above. What's the least possible value for the period? Least possible value, that means you got to find where that cycle begins and ends. Okay, looks like it ends at 6. Does it begin at 0?
No, it's probably beginning at 4.
I would say 1 to 6 looks like a complete cycle before it starts repeating. So if it looks like it goes from 1 to 6, what's the period? Okay, so the least possible value. That means that in this interval from 1 to 6, there's nothing in here that repeats. So the least possible period I think you could have just written a 5. I think it's a 5. In physics, we use the letter capital T to represent period. Kind of bugs me. I don't expect you to have to use that in this class. In physics, we will. So those of you that are headed that direction. Period is a T. Maybe. T equals 5, yeah. But here, I haven't seen that yet in this class. So using the function g and the period found in example 2, find the following values. So this is kind of interesting. They want to know what is g of 14. Using the fact that it repeats every 5 counts, right? So if I want to find g of 14 and I know g of 9, I could click out kind of 5 times and I could see, hey, that's going to be back to g of 9. Can you agree with that? Or do you understand what I'm saying? Okay, so let's count it out to 14. Okay, so we're at 9. What happens at 10? It's still out. Okay, still going across. Okay, we got 2 clicks across, and then what? It drops down 2. By the time I get to 11, I'm down 2, and then what? Okay, so 12, 13, and then what? 14, I'm back at 7, right? That's what I was trying to tell you. If this is repeating every 5 times, then at g of 9, I can tell what would happen 5 times later, g of 14. That would be 7. Okay? It's going to be 7 again. I could carry it out. But now here's where things get yuck. Because the next option is g of 72. So there's got to be a better way, right? I tried to get you to count it to 14 because I feel like that's close enough to g of 9. Okay? But by g of 72, I don't want to still do that. Do you see what I'm saying? Okay.
Can you just divide it by 5 and then take the difference?
And then take the difference, yes. So 72, if I know the period length is 5, then I can take 72 and divide that number by 5, which is going to be what?
14.
14, okay, with a remainder of 2.
So it'd be 2 from the...
So it's going to be 2 from the beginning. So I'm looking here at f of 2, which is 6. Okay, so everybody catch that. G of 72 is equal to 5 times 14. Let's do 14 times 5 instead. I like to put the cycle link through the period in parentheses. So 14 times 5 plus a remainder of 2. You with me? Well, this information here, the 14 times 5, that's repetitive as all get out, and it really doesn't make a difference here. So g of 72 is equivalent to g of 2, which by reading my graph, I can tell is 6. Can you see how that worked? Okay. Now, how do we do g of negative 17?
Same way we did 72.
Same way we did 72. Okay. But I'm not going to have negative information up here. So given the information in my table, I've got positive numbers up here. 3 positive, 3 positive, and how many would you have to take away from a positive 3 to get a negative 17? How many would you have to take away from a positive 3 to get a negative 17? 20. You'd have to take off 20, right? So what if I said g of negative 17 is equal to g of 3 minus 20? This is in a period of 5. So 4 times 5. This is pretty out there. Okay, so we got to make a negative 17, right? But my graph contains positive information. Can you see that? So I want to look at G of a positive 3 because the period is 5. I can find a 3 minus 20, and that would give me the negative 17. And again, the 4 by 5, that's the period part that I'm able to skip because it's repeating. So G of negative 17 is actually going to equal G of 3, which is what? 7. So could we go back to letter A and write a better statement for that instead of popping it out a million times? What could we call G of 14? 2 times 5, so 2 periods, plus what? Plus 4 left over. In other words, G of 4, which is 7. Okay, that could have been a way that we found it based on our table. Are we doing okay with this? A little bit? It's a pretty complicated thought process. Yeah. Yeah, so let's look at this next page. This is example 4, very similar, okay? This is a table of values, but these table values are the only values we get to use, okay? So we're going to have to operate based on only 4 numbers. It says the graph of H is periodic with a period of 5. So that means this cycle is going to repeat every 5 numbers. Okay? Values of H are shown at selected values of X. Find the following values. Okay? So given this table information, 1, 3, 4, 7, those are our only numbers we get to play with. We also know that there's a period of 5. How do we take these 4 numbers, plus the fact that there's a period of 5, and we equate negative 2. So how do I make a negative 2 given input 1, 3, 4, 7? Got to make a negative 2. And my period is 5.
1 minus 3.
Keep thinking. Keep thinking.
Would it be the...
Try to get a negative 2. So one of these numbers plus 5 or one of these numbers minus 5 puts me at negative 2. There it is. 3 minus 5. Okay. So H of negative 2 is going to be equal to H of 3 minus 5. 5 being my period. If I start at 3 and I hop backwards 5, then I land at H of negative 2. Well, the negative 5 business, that's my period. So really, H of negative 2 is equivalent to H of 3, which is 0.
So we're trying to make the inside thing equal the number.
The other inside thing. But only given these values and the period. Mm-hmm. Okay, so let's try letter B. H of 6. How do I land at 6 given a period of 5 and given 1 and 5, right? So H of 6 is equal to H of 1 plus 5, which I would probably not look at that 5 anymore. That's my period. H of 6 is going to equal H of 1, which is negative 2.
So we just ignore the
Whoa.
Once you get it, you're cycling through that many 5s, okay? What's the leftovers, right? Oh, we're getting better. H of 9. So H of, hold on. H of 9, let's start on that inside. H of 9 is going to be what plus or minus 5?
4.
4 plus or minus 5, right? So 4 plus 5 would make the 9. So again, I can throw out the 5 because I know that it's cyclic. H of 9 is going to equal H of 4, which is what?
3.
Okay, so H of 4 H of 4 is 3. So now I'm looking at H of 3, which is, what's H of 3? It's not 4.
Oh,
0.
I was looking at the, okay, never mind. I was wrong.
Yeah. H of 3 is 0. So H of 9 is 0. How'd we get the 9? We said I've got a period of 5. 9 divided by 5 is 1 with 4 left over. So I'm reading H of 4, which happens to be 3. H of 4 is H of 3. H of 3 is 0. Everybody kind of walking through that. Okay. How about this one? H of 5 times k minus 3, where k is an integer. K could be 2. Okay, so here's the deal. If you get rid of the 5k, we've been kind of throwing that piece out and saying, okay, this is going to equal h of negative 3. And I agree with that. Except on my table, there's no negative 3. So how do we create the negative 3 situation?
3 minus 5.
Okay.
Wait, oh yeah.
Okay, so Jenna's saying if I use my period, which is 5, and I know I'm trying to come up with negative 3, h of 7 minus 2 times 5, 7 minus 10, makes the negative 3. You following that? So h of negative 3 is equal to h of 7, which is 2.
Where'd the 7 come from?
Yeah.
7's a value in my table.
Can you just figure in the value?
You could use any of these values, but you've got to be able to come up with a negative 3, and you're operating on the period, which is 5. Multiples of 5. Okay? So if I do 4 minus 5, I get negative 1. Not quite enough. 7 minus 5, I get negative 2. But if I do 7 minus 10, I make the negative 3. So k must be 2. If k is 2, then we're working here. Huh?
Does that get longer?
No. And there are lots of different ways you can go with this. Okay? Your brain, whenever you're doing your worksheet, may pull something completely different than what I did. You've got this combination of numbers, and you've got a set period. And you've got to manipulate it in order to figure out what your output would be. Okay? It's kind of like a game. And what you're trying to do is match the input value that you see here. Okay? All right, let's go on. It says it's useful to have notation to model this phenomena. A periodic function starts with a basic pattern and translates the pattern repeatedly over its domain. So as a result, we're able to consider a periodic function as a horizontal translation of itself. And that makes sense. I take a function, I move it. I move it, I move it. It's almost a tessellation. Did y'all work tessellations in geometry? Okay. Kind of is feeling like that. In example 4, the period of h was 5, meaning that we could translate the graph of h horizontally 5 units and end up with the same picture. This means that the function satisfies the following equation for all values of x. H of x equals h of x minus 5. H of x minus 5, minus 5, minus 5. Okay. Example 5 says, the graph of f is periodic with a domain of all real numbers. 2 full periods are shown. Do you see them? Okay, I can see basically 2 cycles. Find all input values of f that yield an output value of 1. Find all input values of f.
2 and 6.
Okay, all. All input values of f.
1, 2.
Okay, so what are you doing? What's the period?
2 plus 4 times times 2.
Perfect. So x is going to equal 2. You know this happens at 2. You know it happens again at 6. You know it happens again at
4.
12.
18.
10 and 14 and 18. So what's happening every time? You're adding that period of 4 to whatever integer you're trying to plug in. So the x values are going to repeat. It's going to be starting at 2 plus 4 times the number k, the integer. That's how they write it. 2 plus 4 times the integer. So that's going to, every output of 1 occurs at 2 plus 4k. Okay. Let's try another one of these. What is my output of 4?
3.
Output 4?
Oh,
1 plus
output
4
4.
times.
Right, 1 plus 4 times k. Right? That happens at 1. That happens again at 5 and at 9. And where's the next one? 13, 17, 21. Okay, so 1 plus 4k would be output of 4. I don't know where the 3 came from.
I
We were doing
misunderstood
like
what
the
you
x
said.
was 4.
Oh,
That's what.
output of 4.
Yeah.
Yeah. Okay. All right, so this is a real life situation. I have seen one of these questions on a potential test. Okay. So it says the figure shows a large clock mounted to a vertical wall. Okay. The clock has an 8-inch long moving minute hand. 8 inches for the minute hand. That means that the radius of this clock is 8 inches. Okay. I would pay attention to that.
Physics books, sorry to interrupt.
Physics books.
Textbooks.
All right. Thank you, Hayden. Right there. Just right there. Perfect.
Bye, Hayden.
Bye, Hayden. Okay, the radius of your clock is 8 inches. The center of the clock is 120 inches directly above the floor. So the center of the clock is 120 inches from the floor.
The bottom of the clock is 112.
Okay, so the bottom of the clock, I like that. True, it says so. That means the bottom of the clock is 112 inches from the floor. That's fair.
Not necessarily because the hand doesn't go all the way to the end.
It does. It does. Let it be. Let it be. Let it be. Okay, so at time t equals 0, the minute hand is directly pointed up at the 12. However, the clock is not working properly, and the minute hand is moving twice as fast as it should. So every cycle is now 30 minutes. Every cycle is 30 minutes. You with me? Instead of it being an hour. Thus, yeah, I would. Period is 30 minutes. Period is 30 minutes. It should be 60 minutes. The more you know. However, okay, the next time the minute hand points directly up is at t equals 30 minutes. As the minute hand moves, the distance between the end point of the minute hand and the floor periodically decreases and increases. Periodically, right? So we're measuring this distance. Sometimes it's 128. Sometimes it's 120. Sometimes it's 112. And it's a periodic change. Okay? They have given you a periodic function below. This is part A. Periodic function models the distance in inches between the endpoint of the minute hand from the floor and the period as a function of time in minutes. It looks like a sine wave. Imagine. Okay. The graph of H and its dashed midline for 2 full cycles is shown. 5 points, F, G, J, K, and P, are labeled on the graph. No scale is indicated and no axes are present. So you have no idea what these numbers are. You have to decide. Determine possible coordinates for the 5 points. I will give you a hint. I let F be 0 at time t equals 0 because it was the highest. What was its distance? 128. So F I located at 0, 128. 128 inches. That was time t equals 0. Clock was straight up. Right? By the time, okay, so he's saying same for P.
So it would be by 120.
You got
30 minutes. So by the time we get to P, it's gone 30 minutes because remember the clock doesn't work properly. So it's gone 30 minutes by the time we get to P and we're back to 128. Okay, so if this is 0 and this is 30, time t equals 30, then where's J? Okay, J feels like a solid 15 minutes. And by 15 minutes, it should be halfway around. So how far is it?
112.
112. There's your number, Truett. Good. Okay, so in this intermediary place at I don't know, it looks like it should be 15 minutes on the clock, but it's really not 15. It's really 7.5. 7.5, it's located horizontally, which was the 120. The center of the clock is 120 feet. Okay, so travel past 15, 7.5 around the other side,
22.5.
22.5, and we're 120 again. Did y'all see this? Everybody okay? Yeah? Okay. All right. Part B says, refer to the graph of H in part A. The t-coordinate of G is T1, and the t-coordinate of J is T2. On the interval from T1 to T2, so that's talking from here to here. Which of the following is true about about H? What's it doing?
It is concave up.
Is it negative?
Decreasing. It's decreasing and increasing.
It's through the fact.
It's increasing and decreasing.
Okay. It is increasing.
Positive.
It's positive. How do you know it's positive?
Because you're still increasing.
Does the number say it's positive?
You're increasing in time.
Does
It is
all-
concave up.
Positive.
You're increasing.
Oh, because the time is positive.
And because it hasn't gone below the x-axis, right? So we located that at 120 to 112. We're way above the x-axis. So I would say H is positive, but it's trending in the downward direction, so it's positive and decreasing. Okay. H is positive and decreasing. If you look at this, we marked this as 128. We marked this midline as 120. We marked this bottom line as 112. So where would H be negative? All the way down here. Right? If it's below the x-axis, it's negative. Do you understand? These values are all positive.
Yeah.
Ground level would be 0. Unless this clock has fallen off the wall through the ground,
Thinking about
the values of H.
oh.
They're positive,
Okay.
but from G to J, they are decreasing, right? It's going from 120 down to 112. So they're positive values because it's still above the floor, but they're decreasing. Those are the values of H. Now, the next question, part 3, says describe the rate of change, which rate of change means my little tangent lines, right? So if I'm drawing tangent lines on the graph between G and J, what direction are my tangent lines? They're negative. So the rate of change of H, rate of change,
AKA the slope.
aka the slope of the tangent line, of H, what are they? Is negative. But what's happening? They are increasing, right? It's decreasing at a increasing rate because they're becoming less negative. They are becoming less negative. When they are becoming less negative, they are increasing. When the rates of change are increasing, our picture is concave up. Decreasing at an increasing rate. Slowing down. That's some first semester stuff. Okay. All right. I want you to, before I let you go, I want you to go look at your picture on the back page of your worksheet. Find number 10. You've got a toy car in a situation very similar to the clock. Okay? And I don't have this graph where I can access it really quickly, so I'm just going to freehand it like this. They've got F up here, and then G on the midline, and then J down. Okay? I think it will be very, very helpful if you can understand that F begins at 4 seconds. 4 seconds. It says a toy car travels around a circular track as shown below. Center of the circular track is 20 inches away from the wall. At time t equals 0, the distance between the toy car and the wall is 0 inches. The car completes one full lap every 8 seconds. Okay, so one full lap every 8 seconds. As the toy car travels around the track, the distance between the car and the wall increases, decreases, decreases. Okay, every 8 seconds. So what you've got here is the dashed midline. If we let F be 4 seconds, that felt like to me the furthest the car was away from the wall. Can you see that? So I'm letting the wall or the midline be 20 inches. Because that allows J to be 0 inches. Point J seems to be when it's on the wall.
So point F is.
So F is going to be at 40 inches. Now, when is it furthest away from the wall? At time t equals 4 seconds. And it's going in a counterclockwise or a clockwise direction, right? So if I travel back, that means this would be 2 seconds. It's going to be 20 inches from the wall, which puts it at 0 seconds, 0 inches from the wall. So those two make sense. So for F, let that be 4 seconds. It's 40 inches from the wall. That's the furthest outest point. By the time it gets to G, how many seconds are we talking? 6 seconds at G. And G is going to be 20 inches away. And by the time it cycles back 8 seconds through, J, it's back on the wall. So it really helped me to extend this picture, extend my graph to the left, noting 0 and 2 and starting with F at 4 seconds. Yeah? All right. Good luck.
Thanks.
Mm-hmm.